So I would like you, and if you'll notice on your Slido screens, to answer the first question, which is rank from greater to lesser the achievements in aerospace engineering. I don't know why it is giving you there we go. Now, this is a little bit of an experiment. So next hour when I do this, we're going to do it in such a way that I hide the results from people. And we'll see if we get a different result. But yeah, you're welcome to rank any of those as you think, one or all. Have a discussion briefly amongst each other. Again, if you have any questions you want answered, put them in the Q&A. So according to this, 26 of you have responded. 28 of you, 29 have responded to the poll. Up to 40. So those of you who just walked in a few minutes late, sit down, follow the link to slido.com or the QR code if you can get it to come up, and answer this. As you see, and I said next hour we're up to 49 people, so we're not going to be far more than that today. Next hour I'm going to do it, and we're going to hide the results while people answer it. See if it changes the. So right now, those of you who've responded, and based on how you responded, number 1 is the gas turbine or rocket propulsion system, followed by the internal combustion engine, 3 computers, 4 Cayley's glider, and 5 the helicopter. I expect the helicopter to be at the bottom, by the way. But it doesn't have to be. And if you can sit at tables with other folks, that's great, because we will have some other discussions coming up. After you've done answering it or filling that out, if you want to ask any questions for the live Q&A, it is anonymous, so if they're silly, it won't be tied back to you unless you start blushing when I read them out. Okay. Oops. Don't know why that did that. It's done it to me again. Okay. Decided. Okay, so number 1 and 2 are pretty close. So they are the gas turbine rocket and the internal combustion engine. Number 3 is computers, 4 is Cayley's glider, and 5 is the helicopter. So let's forget the helicopter for just now. Let's start with Cayley's glider. And why Cayley's glider really is important, and probably more important than most of us realize. So this is his glider. Anybody remember what it is that's special about George Cayley's glider? Those who watch the videos, the rest of you can remain quiet. Yeah. So with the distinct, what we would now call a fuel, the primary lifting surface, and then a tail as a control surface that handles both longitudinal and directional stability. And in a sense, it's the first time someone has visualized, not built it and actualized it in the visual, and then built it, actualized, what we know of as a modern aircraft. So every aircraft, fixed-wing aircraft you see flying today, save a few, you probably can think of a few, basically apes this design in one way or another. Now, there are variations on this. There's the canard configuration, where instead of having a tailplane, we have those in the front section of the aircraft. And that's what the Wright brothers aped for the Wright Flyer. They have a canard configuration. In general, this is the aircraft that sets out the two basic aspects of gliding flight, which is lift control. Now, what do we add for sustained flight? What's that third aspect that we have to care about? Yeah. Propulsion. Okay, so as you said, the other two most highly, the propulsion systems. Now, I put up internal combustion for a reason. We talked about it, I think, a little last week in one of the sessions. Why is it that internal combustion engines, by the way, a gas turbine engine is actually a form of internal combustion. We think of internal combustion engines, what do we think of? What type of engine? Yeah, a reciprocating piston in most cases. But what is it about an internal combustion engine that makes it ideal for aviation? Or for spaceflight, for that matter? Yeah, so they have very, very high power density. So an internal combustion engine is an engine that uses its combusting fluid as its working fluid. I.e., I take oxygen from somewhere, be it a tank, a propellant system, or an oxidizer, or the air, combust it with the fuel, and the resulting fluid, I extract the energy and work directly out of. So, in the case of a reciprocating piston engine, use the piston, extract the work, shaft, and the case of a rocket or a ramjet, I can expand that through a nozzle and create direct thrust, or I can expand it via a turbine in a nozzle, turbojet, turbofan, turboprop, that I can use to press or do other things with, or I can take all of that through the turbine and put it into a shaft, turboshaft. Versus an external combustion engine, where we combust a fluid, then we transfer that heat to another fluid, and we extract work from that. Can anybody think of a classic external combustion engine that was common at the time of Cayley and still very common at the time of the Wright brothers? A use of an external combustion. Yeah. Yeah, but any specific type of steam engine that was. Yeah, steam locomotives on railways. They were really common. Unfortunately, that whole process, that heat exchanger, all of that requires a fair amount of weight. It's also quite bulky. And to give you an idea, a steam locomotive might work at 300, 400, 500 pounds per square inch. You know, we're talking 20, 25 bar, which isn't a lot. You can get extremely energy-dense, power-dense steam external combustion propulsion. You're talking at a couple thousand bar. So 3,000, 5,000, 10,000, 20,000 psi type stuff. And they become extremely compact. Of course, think about it this way. A modern engine like a Trent XWB at top climb, the internal pressure, the overall pressure ratio, 55 to 1. So it's 55 times higher inside that engine than outside. Not quite that high at sea level, but those ratios, those differential pressures are what we're seeing. Okay, so what's the difference, do you think, between a gas turbine or rocket and our standard, what we think of as an internal combustion engine? What makes that a big change, a big leap in history? So we'll go, actually, back in time for a bit. And we'll go to this one. Maybe. What's the difference between this? This is obviously something very crude. And this is actually an external combustion system. But what's the difference between this, Hero's engine, which is effectively the first jet engine drawn in history, and a piston prop? What's the biggest difference here that will usher in why we use jets and rockets for high-speed, high-altitude type flight? What is it that changes here that allows us to get an even higher power density out of our system? What have we done? Anybody want to hazard a guess? Yeah. They all use Newton's third law, but it's how we use Newton's third law. Absolutely. So, in a piston prop, we use that working fluid. We extract the power out of that to turn a shaft, which turns a propeller. That propeller then accelerates the flow. So our propelling fluid is out in the atmosphere. You know, same with the helicopter's rotor blades, right? Our propelling fluid is that atmosphere that we're capturing with our rotor or our propeller. In the case of a pure jet, not a turbofan, not a turboprop, but a turbojet, a ramjet, or a rocket, our propelling fluid is our working fluid, right? So all of that energy in that propelling fluid is now available, working fluid is now available for propulsion. Yeah, of course, we're never going to be perfect at extracting it, but we're accelerating it through a nozzle. Now, what's two advantages of that? One is we can get that going a hell of a lot faster than we can through a propeller. Reason why is we're working with much, much higher pressure differentials. So as I said, we're talking 50 to 1 in a modern commercial gas turbine, propeller 1.2 to 1. So we can accelerate that a lot more. That means we can get a lot more kinetic energy. Yeah, we might lose some efficiency, but it means we can go a lot faster. When we talk about propulsion later in the semester, we'll talk about that ratio and what that means and how it works. But what was the other advantage? Now that we're using our working fluid as propelling fluid, what can we do that we couldn't do before? Spurs. Yeah. Yeah, we carry our fluid with us. We don't need that fluid out in space. Now, next week, when we talk about the atmosphere, we're going to talk about the fact that there is an atmosphere in space. It doesn't just disappear. And even 1 billion miles from Earth, 1.6 billion kilometers from Earth, there is still an atmosphere. Yep, we're in the inside the heliopause. There's a solar atmosphere. There's a solar wind. But it's not meaningful enough, unless we do really intense things with it, to give us propulsion. So we carry our working fluid. So that's what changes that. So each of those, I would say and argue, is probably equally important. We couldn't have gotten to the second one without doing the first one. Okay. So then we talked about computers, I believe it was. Yes, computers was the next one. Anybody want to fathom why they thought, anybody here want to own up to ranking computers as top? Or above the other things we've talked about? Yeah. Anybody want to offer up why they put that up there? Yeah. Yep. Okay. Yeah. Yeah. I mean, the classic one that you all probably have seen and some of you may own that doesn't work without a computer is your UAV multi-rotor. The 4, 6, 8 rotor small UAVs. If you had to fly those truly by hand, almost no one here could do it. I wouldn't say no one, because there might be someone here that can manage to do 6 sticks, 6 throttles at the same time, or 4 or 8, but I haven't met anyone that can do it. They require computers. Now, when you get on an A220, an A320, an A350, do you think you need computers for that aircraft to fly? You don't. Except for the engines. In fact, the aircraft, yes, if the electrical system totally fails, every aircraft built since developed since the 777 commercial aircraft would have a problem. A320, believe it or not, the early ones, there was a mechanical linkage to the rudder and a mechanical linkage to the horizontal stabilizer. But those have now disappeared. But they don't need the computers per se. They can work in what's called alternate law, and which is raw law. Yeah. Oh, yeah. We use computers for all sorts of things. But commercial transports, for lots of valid reasons, need to be flyable without the computers intervening. Now, that doesn't mean in reality they are. Because what's the weakest point in that system? Yeah, the Mark I human being. What happens if you're flying an A330 over the South Atlantic? I believe it was still South Atlantic at that point. Maybe not. Go in a thunderstorm, and your pitot tubes freeze up. What does the computer do? It complains. It goes, I can't do this anymore. I am shutting off. It is your problem now. Or if there's a circuit breaker that keeps tripping on the rudder because there's an electrical fault. And instead of just isolating all the other control computers and turn them off, the computer goes, well, I'm on. Goodbye. You've turned the power off. Now, that's all well and good, except for what happens. I've gotten very used to flying my A320 or my A330. I know that if I pull the stick back, it adjusts the speed for me because it's speed stabilized. Or that if I move the stick slightly, put enough pressure on the stick to the right, it gives me the same roll rate no matter what the flight conditions are. I've gotten really used to that. I also know that because of the design and Hawker Siddeley Trident and Bach 7, that Airbus has implemented a hard envelope protection on longitudinal control so that it won't allow me to stall the aircraft. So I've gotten really used to that. All of those have now just disappeared. So instead of the resolve for giving me a given roll rate, it gives me a fixed control surface deflection or a pitch deflection. So the aircraft now behaves totally differently. Uh-oh. The one thing you never want to hear from a flight crew member is, what's the aircraft doing? And of course, you build up and you have human factors and people don't realize that the guy's holding back because that's turning the stall warning horn off because it's the speed's now descended or whatever. We have those accidents. So, obviously computers make things a lot safer in many cases. They make things a lot more efficient. In fact, the biggest area we've seen advances is in propulsion. Going from the old mechanically controlled gas turbine engines to the fully digital, full authority digital electronic control, FADEC, gas turbine engines has improved the reliability of our gas turbine engines by an order of magnitude. Where before, we might have gotten 2,000, 2,500 hours between overhauls, we now can leave a gas turbine engine on the wing in some cases for 50,000 hours. That's not 50,000 hours just sitting in a field. That's 50,000 hours flying in the sky. Now think about that. 50,000 hours. That's a lot of time. An average aircraft, commercial aircraft, may fly 3,000 hours in a year. That's 15 plus years on the wing. That's because of computers. The same thing with your car. All modern cars, the engines are digitally computer controlled. And they tune it, they make it more efficient, but they also means you can go 20,000 miles, 32,000 kilometers without changing the oil. The computer will tell you if it needs it. So amazing differences. And of course, it's allowed us to do things that we could never have done before. Anybody know why the F-16 is perfectly stable longitudinally? It was horribly unstable longitudinally. And when the computer crashed during an air show, the plane crashed because it can't fly. Anybody know what that aircraft was? The U.S. announced it in 1990 that they had it, or 1989. It was the F-117 Nighthawk, the stealth fighter, as they called it. So, yeah, to get those low observable characteristics, the aircraft truly was unstable. And they had one crash in an air show in Baltimore, and it crashed. That there wasn't a classified part. So the U.S. government seized all of their property, burned it all. They got one photograph out. The house didn't burn down. Only part of it did. But because of it. So, but yes, so we use that all the time. Now, things like Eurofighter, F-22, F-35, they are unstable now. We have gotten there. Turns out the F-16 has directional stability issues. and the computer won't let you fly that way. B-2 bomber has all sorts of weird corner cases. Computer won't let you fly. Can anybody think of an aircraft that has an issue, really kind of famous, ugly looking thing, has an issue where they've allowed the computer to allow the pilots to crash it? Notorious for what's called ring vortex state. Rotor, really high power density out of the rotors. If you descend too quickly, you'll get what's called ring vortex states. Problem with all helicopters, but it's a real problem with the Osprey. And all of a sudden, instead of being nice and a nice rate of descent, the aircraft is just in free fall. And it's something that we can, with computers, put a hard envelope protection, keep that from happening. But the US Marine Corps decided that since Marines tend to get shot at when they're in these things, it's better to guarantee that they die in a ring vortex state, then maybe they'll get shot down. Because we don't know where the ring vortex state is, so they've just allowed it to be done, and they said, we'll train the pilots to avoid it, to recognize it after it's set on. They've since modified the flight control system. Okay, helicopters. Now, why do you think I put helicopters on there? What is it that helicopters do we've not been able to do before? They really did change things. Yeah. They can where? So there's lots of things out there that we do today that aren't possible really without helicopters. Turns out, modern super tall skyscrapers, the way we build them, the way we air condition them, you need helicopters for those. Some of the modern ski lifts, can't really build them in places that would build them without helicopters. But it's also search and rescue. You get stuck out in the sea, they can send a helicopter out and get you. Before that, take your chances. But yeah, I don't think they're quite as big of a deal. Okay, so there are some questions. What does a rocket engine have to use as an igniter? Good question. We'll talk a little bit more about rocket engines in a little while. So when we talk about rockets, about why we have boosters, strap-on boosters for rockets, why they were developed. The first rocket with a strap-on booster was the R-7, i.e. what we now know as the Soyuz. An interesting thing, you know how they light the main engines on a Soyuz rocket? Use giant matches. They are literally electronically ignited matches. Big wooden things that they stick in. But we use all sorts of things. They use spark igniters. In the case of hypergolic fuels, they just mix the two fuels together. Or if it's a monopropellant, just run it over a catalyst and it just combusts. How does an electric turbopump work on a rocket engine? Well, it's not really an electric turbopump, it's an electric pump. Turbo pump is a pump driven by a turbine. So what we do in a rocket like the RS-25, the engine that SpaceX is developing for the Super Heavy and all that, is we combust fuel and oxidizer in a separate little engine, and we expand that through a turbine to compress and pump the liquid fuels. And that's how a turbopump works. An electric one, we just have an electric pump, high efficiency pump to do that. Now, depending what your fuel is, that ranges from hard to insanely hard. So to give you an idea, the nominal chamber pressure of an RS-25, a Space Shuttle main engine, is over 3,000 pounds per square inch. And I'm using that because that's what it's nominally rated in by the US. We can figure out how many bar that is. It's a lot, because remember, 1 bar is 14.7, 15 pounds per square inch. So you're talking 2,000 bar, right? So we have to compress liquid oxygen and liquid hydrogen to that from ambient, because it's not stored pressurized. Yeah, the tanks are a little bit pressurized, but we don't want them to burst. We want them to be light. So we have to compress that to ambient. what they say about compressing liquid hydrogen, it's like trying to compress ping pong balls. Except for they're really, really cold and make everything extremely brittle. Oh, and hydrogen likes to get into metal. If you have any free things, hydrogen goes in there and brittles your metal. So we've got to do that and not have it disintegrate on us. So it's not exactly an easy thing. If you got kerosene, pretty easy. Liquid methane's a little bit harder. Liquid oxygen's pretty nasty, because what does oxygen like to do? React with everything that hydrogen doesn't. So it likes to react with metal, and believe it or not, put aluminium or titanium in an oxygen environment, add a little bit of heat, and it combusts quite readily. So that's what works. So we just use an electric motor, really, really high power density electric motors, and electric motors can be extremely high power. Got something cold, liquid oxygen to it, you can cool it down, and it's much, much more efficient. So our efficiency may go from 70% to over 90%, 95, 98, 99, close to 100% with some of those. Okay? Okay, next poll. And you can see it on your screen, and it's not going to let me show it up here. It on your screen. This is the "Did I actually watch the videos?" question. Is this? And you shouldn't see the results, so let's get out of there. Sorry, it is letting you know. And yes, you can talk amongst yourselves. It's really obvious? Is that what you said? Well, I mean, technically, one of the options, not the one that I call correct, is correct if you look at the bottom right-hand corner. There is a golf course in this screen. That isn't what it's famous for. Might want to use that if you're uncertain about the other bit. Just on this, there's an old joke about what's the difference between the U.S. Army and the U.S. Air Force. And why are Army bases crap and Air Force bases really nice? Specifically, why are their golf courses crap and U.S. Air Force golf courses are nice? And that's because when the U.S. Army builds a base, a fort, build the base, and then they, with whatever money's left over, build a golf course. The U.S. Air Force, on the other hand, builds a golf course using all of the money, then goes back to Congress, says, well, we can't finish our base, we've run out of money, give us more. Another interesting thing, the U.S. Army operates 10 times more aircraft than the U.S. Air Force. So for every fighter jet, transport aircraft that the U.S. Air Force has, the Army has 10 aircraft. They're all helicopters. So there are far more military helicopters built than any other military aircraft. But there are far more commercial transports built than any other thing. F-35 is supposed to be 3,000, 4,000 aircraft. That's a big run for a fighter jet. In the case of been built, A320, 737, we're going to be at 20. And then you have the 172 later. Has everybody figured out what this one is? So this is what people have answered. It is technically the home of a U.S. Air Force golf course on the bottom of the screen, but that's not primarily what it is. Anybody want to say what this place is, what it's called? Anybody remember from the video? You can go there. There is a museum. And then if you go there at the right time, you can book, or book ahead, you can book tours on it. It's right off the end of a runway on an active U.S. Air Force base, so it's kind of restricted otherwise. It's unassuming. It's the first aerodrome, airport, home of the first flight school. And now it's just a field in rural Ohio. Well, semi-rural Ohio. Lots of places that are historically in aviation aren't much of anything. Interesting. So Solstice has crashed. See if we can get it back. Aren't particularly. Okay. Any other questions before we move on to the next bit? So. Why do rockets have vacuum-optimized engines on stage? Interesting. Again, we'll talk much more about it. The engines themselves, what is optimized, and I don't know why this is the wonderful network in here. The engines themselves, what is optimized is the nozzle. So you're going to learn when you do compressible flow next year that when you have supersonic flow, it does not automatically end up the same pressure as the surrounding atmosphere. So if I blow out of a balloon or a 1,000 exhaust nozzle, that engine, the exhaust, is subsonic. It's going really fast because it's really hot, but it. And so by definition, the pressure exhaust flow is exactly the same as pressure. Because if it isn't, you have to have a discontinuity. That's called a shock wave. Get a shock wave, that means the pressure information can't flow across that, and therefore it has to be supersonic. Okay? Because sound is defined as the isentropic, no energy generating transmission of pressure. So I am talking, and there are these nice isentropic pressure waves going out to your ears, or via the microphone, speakers to your ears, and that's what is sound. Anybody heard a shock wave? Sonic boom, or from an explosion? Yeah, that's supersonic. That's generating. So that's different pressure. You will notice a massive change in pressure across that. It feels like it hits. Okay? So what's the ambient pressure at liftoff, roughly? For rockets, what's the ambient pressure? Yeah, it is spherical, roughly, for most rockets. Pretty close to 1 bar. Sites, Kennedy, Vandenberg, Curlew, they're close to, okay, Baikonur's a little bit higher on the steps of Kap, but they're pretty close to sea level. They like them next to the sea for a good reason. Anybody know why launch next to the ocean? Yeah. Yeah. There aren't a whole lot of people living in the ocean. Things go wrong, we launch out. In fact, in the US, it's required that you launch out over the ocean. So from Kennedy, that's great. You're launching at 28 degrees, 20.5 degrees, down to 0 degrees, maybe up to 52 degrees. You're not on anything. Case of Vandenberg, where they do polar launches, 90 degrees, 3 degrees, which is sun synchronous, roughly. To the south, because the north is land. They launch to the south. But they like doing that. So it's close to 1 bar. We want a nozzle that's close to 1 bar as possible. But what that means is as we ascend, we're coming out at way too high a pressure. So we're losing efficiency having that expand afterwards. So at higher altitude, second, third stages, we're closer to vacuum. So we put a vacuum nozzle on it. So it comes out at a much lower pressure. We can't get it to zero, but we get it a lot closer to zero. The result is, at sea level, it's overexpanded. Instead of the bloom out, come in, compress in. Look at the exhaust of an overexpanded nozzle, you'll see shock waves form. They're called shock diamonds. And you'll see that if you have a space shuttle main engine, which is a vacuum engine, because it's really designed to do all this work at altitude, those have diamonds. You can see it form in when it comes out at sea level. But up at high altitude, 100 kilometers, 200 kilometers, it doesn't do that. Versus solid rocket boosters, they have a nice straight out. That's why sea level and vacuum nozzles. Okay? How does a rocket's control surfaces work while they land? And how does that compare to an aircraft control surface? Okay, so most rockets aren't designed to land. We have a few of them. And it all depends what they do. So some of our rockets have physical fins for control, and some of them are totally propulsion controlled. So if you ever Falcon 9 on landing, or the primary control on landing is actually the rocket nozzle. The great fins add stability, but the control is from the rocket. Yeah. And basically, it's just like if you've ever tried to balance a pool cue. You balance a pool cue, you can move your finger back and forth just slightly and it'll hold, and you just do that. Anybody know what the first rocket was to take off vertically, fly horizontally, and land vertically? Yeah. Nope. Going back almost 30 years. McDonnell Douglas DCX, and it was a prototype for a single-staged orbit launch vehicle Douglas was trying to sell NASA. NASA, as usual, was not interested because it worked. They don't like things that work. They were enamored with a lifting body configuration that took off horizontally, flew into space, and returned horizontally. Needless to say, that didn't go anywhere. DCX, DC Clipper, was what it was going to be called. McDonnell Douglas didn't want to spend the money to develop it on their own, and they parked it. Engineers actually left, but cut their teeth on that, and went to work for companies like SpaceX and Blue Origin. And by the way, it was a NASA program, so all of that documentation on it was available to whoever American company wanted to use it. Okay. Why do rockets have a throttle down, maximum dynamic pressure? How does max Q, maximum dynamic pressure, affect the flight profile? So, two things. Dynamic pressure is the pressure you feel from moving air. Obviously, there's two reasons we want to minimize that. One is drag, because obviously drag goes up with dynamic pressure. Dynamic pressure goes up with the square of velocity, which is fluids. So we don't want to waste energy on drag. The other thing is we have to build our structures to withstand that force. So what we do, we throttle down through that, minimize the amount of pressure, and basically what we're doing is we're trying to keep it from exceeding a certain amount as we go up in the atmosphere. Because of course, pressure falls off, dynamic pressure, 1/2 rho v squared. Rho is density, or 1/2 pressure times Mach number squared. We want to keep that Mach number from accelerating too much until our pressure falls off. Exponentially with altitude. We'll talk about that next week. So that's why we throttle down. What do you think is the worst designed aircraft that was put into production? Depends how you define. We'll talk a little bit more about that at the end of the semester. There are some aircraft out there that are really famous that were actually probably really bad ideas for lots of reasons, and some other aircraft. We can talk about bad design options on aircraft too over time. Okay. Are we expected to know all the equations that we were talking about? So the equations we talked about today, I will come up over and over again. So when we get to those portions of the unit where we have equations, those are the access to. Right? I'm not going to give you equation sheets on the exam, but you can bring them. I don't expect you to memorize any equations. I expect that you will remember many equations. You will remember them because they use them all the time. You will density air in a standard atmosphere at sea level on a standard day is 1.225 kilograms per meter squared. Not because I ask you to remember it, but you will use it so often over the course of the next few years that it will just stick in your head. Right? 101 point something kilopascals for pressure, sea level standard day. 273.15 degrees 15 Kelvin is 0 degrees Celsius. 50 degrees Celsius, they're 288.15 Kelvin is your sea level. And if you're having to use custom units, you will end up remembering those too. A standard day, 59 degrees Fahrenheit, 15 degrees Celsius. 14.7 pounds per square inch. I expect you to remember those, right? We'll talk about when we get to it. Okay. One last activity, and we've actually used it. I will open it. You're welcome to fill it out at a later time. It was basically to talk amongst yourselves of what you thought about when you thought about later than air flight, fixed wing, and space flight, but we've used it all up today, so don't worry about that. Next week, we're going to be on topic 3, which, if I remember correctly, is the atmosphere. Am I correct? Yes. So watch those videos. We'll have a few more questions and polls and the like on that. Of course, this has gone down completely. So thank you very much. The podcast, as soon as I get them up and we edit out all the crap on either side of it, will be up and available for both of them. Thanks, guys.